Imagine intentionally taking a compound, like every single day, that you know structurally is going to begin systematically calcifying your internal organs.
Right, just tuning your insides to stone.
Yeah, exactly. You're taking this substance that will literally prompt your body to start forming these bone-like deposits inside the soft tissue of your kidneys.
Which sounds horrific, honestly.
It does. It sounds like a slow-acting poison, something out of a medieval toxicology manual or something. But the wild part is, the substance we are talking about isn't a poison at all.
Not even close.
It's vitamin D.
Yep.
The exact same compound that is universally recognized as this vital growth factor. I mean, it's the thing we fortify our milk with, right?
Right.
And we encourage kids to play in the sun so they synthesize it.
So they can grow up strong, yeah.
Right. Well, welcome back to the Deep Dive, everyone. We have a truly fascinating set of scientific notes that we are unpacking for you today. And they basically dismantle the way we traditionally categorize, health, disease, and the actual biological materials that build us.
It is a profound set of documents, really, because it forces this confrontation with the reality of biological thresholds.
What do you mean by thresholds exactly?
Well, we operate under this sort of colloquial assumption that nutrients are inherently good.
Right. Vitamins equal health.
Exactly. And that toxins are inherently bad.
Hmm.
But when you look at the actual microscopic mechanisms regulating human health, that binary just completely evaporates.
It just doesn't exist.
No, it doesn't.
Right.
A vital growth factor and a deadly toxin can literally be the exact same molecule. The only variable is the concentration and the mechanical balance within the system.
And balance is the absolute core of the materials we've got for you today. We are looking at this from two interconnected angles, really. First, the internal microscopic architecture of life.
The nucleic acids.
Right, the DNA and RNA, the master algorithms for our entire existence. And second, the external chemical catalysts we ingest to keep that internal machinery running.
The vitamins.
Yeah, the vitamins. And what becomes terrifyingly clear, like reading through these notes, is that a microscopic variance in either of these systems...
Just a tiny shift.
Just a tiny shift, yeah. A single misplaced molecule in a DNA sequence or, an accumulation of a specific vitamin in the fat tissues, it doesn't just cause a mild disruption.
No, it cascades.
It cascades into systemic, catastrophic biological failure.
The precision required for you and me to just sit here and have this conversation is staggering. Yeah. I mean, we are talking about billions of continuous chemical interactions that have basically zero margin for error.
Zero.
Right? And the notes ground this complexity by starting at the absolute bottom. Before we get to genetic codes or, deficiency diseases, we have to look at the structural foundation.
There's basic building blocks?
Exactly. The text identifies nucleic acids as the fundamental, the completely non-negotiable components of every living cell. They are built from these repeating units called nucleotides.
Right, and the breakdown of this nucleotide is where the real architectural elegance begins, in my opinion. We are looking at a three-part structure here.
Just 3 parts.
Just 3. You have a nitrogenous base, a pentose sugar, and a phosphate group.
That's it.
That's it. That triad is the universal prerequisite for biological life. I mean, I like to think of it like a microscopic Lego set.
Oh, that's a good way to look at it.
Yeah, because there is no alternative operating system for living things on Earth. It is wild that nature uses just these 3 basic types of bricks, base, sugar, phosphate, to build the infinite complexity of literally everything alive. It's either this exact 3-part chemical combination or it is just inanimate matter.
Which forces us to really analyze that word from the text.
Yeah.
Essential. Why is this specific chemical architecture so universally conserved?
Right. Why did nature just lock this in and never change it?
Well, if you look at the components, the phosphate group, for instance,
Yeah.
phosphorus bonded to oxygen gives the molecule a very strong negative charge. Okay. That isn't just some random trait, It's structurally imperative. That negative charge ensures that the long chains of nucleotides actually repel each other just enough so that the whole molecule doesn't collapse.
Oh, wow. So it doesn't just clump up.
Exactly. It prevents it from becoming a tangled, useless knot of chemicals. It physically forces the structure to remain elongated and organized.
So it maintains the structural integrity of the chain itself?
Yes.
And then you have that middle piece, the pentose sugar, which the text describes as a 5-carbon ring.
Yeah.
That acts as the central hub, right, linking that structural phosphate to the actual data carrier.
Right, the nitrogenous base.
Yeah.
Precisely. The base contains nitrogen, which is highly reactive. It's capable of forming these really delicate hydrogen bonds needed to link the chains together. But the isolation of these three parts is the key takeaway here.
How do you mean?
Well, you have a structural component, you have a bridging component, and you have an information component.
Ah, I see.
It is a highly modular, highly efficient system. Nature found this specific thermodynamic equilibrium billions of years ago and just never deviated from it.
It really reminds me of the way we build modern computational systems.
Okay, yeah.
Like, you have the immutable physical hardware, right? The silicon pathways, the power delivery systems, they just repeat. And then you have the variable logic gates that actually process the data.
That's a really sharp analogy.
Well, the sugar and phosphate are basically the immutable hardware. They just repeat endlessly, providing the physical framework. But those nitrogenous bases, they are the logic gates.
The variables.
Right. They are the variables that actually determine whether the organism growing from this blueprint is going to be a towering oak tree, a donkey, or the human listening to us right now.
And that separation of structure and data is exactly what allows for the infinite complexity of life. If the entire molecule were variable, it would just be way too unstable to store long-term information.
It would just fall apart.
Exactly. By isolating the variability solely to the nitrogenous bases, the system achieves both incredible stability and infinite diversity.
Which is brilliant.
It is.
Yeah.
And that naturally brings us to the specific application of these nucleotides in long-term storage, which is deoxyribonucleic acid.
DNA.
DNA.
Right. And the text draws a very specific distinction here regarding that middle component we just talked about, the pentose sugar. In DNA, it's a deoxyribose sugar.
Deoxy, meaning without oxygen.
Exactly. It is missing a single oxygen atom compared to a standard ribose sugar. And, when you are operating at the macroscopic level, missing a single atom seems like a rounding error.
Sure, it seems completely insignificant.
Right. But in the context of molecular biology, the absence of that one oxygen atom fundamentally changes the entire destiny of the molecule.
It changes everything about its thermodynamic stability. Oxygen is highly electronegative,
Yeah.
right? It's very reactive. A standard ribose sugar, because it has that extra oxygen, is vulnerable to hydrolysis.
Meaning water breaks it down.
Exactly. It can easily react with water and just break apart. So by removing that one oxygen atom, creating deoxyribose, nature essentially rust-proofed the molecule.
Rust-proofing the blueprint. I love that.
It made it chemically inert and incredibly stable, which is the exact property you absolutely need if this molecule is going to serve as the permanent, unchanging storage place for all the genetic information of a cell.
Which perfectly sets the stage for the discovery of its macrostructure. The notes anchor us in 1953, right, with Watson and Crick's discovery of the double helix.
Right, a huge milestone.
Huge. But the text doesn't just treat the double helix as some fun trivia fact. It heavily implies that the shape itself is functionally tied to this concept of permanent, protected storage.
Structure dictates function, always.
Always. So the structure consists of two long chains, right? With the sugar and phosphate groups forming the outer backbone and the nitrogenous bases pointing inward.
Linking the two chains together like the rungs of a ladder. And we really have to consider the environment this molecule exists in. The nucleus of a cell is an aqueous environment. It's full of water and highly reactive chemicals.
A dangerous place for data.
Very. And the nitrogenous bases, the actual information carriers, they are hydrophobic. They repel water. So the double helix formation isn't just some geometric coincidence.
It's functional.
It is a highly effective self-organizing defense mechanism. The molecule twists into a spiral so that the hydrophobic bases can pack tightly together on the inside.
Shielding them.
Right, completely shielded from the reactive aqueous environment by that tough, hydrophilic, sugar-phosphate backbone on the outside.
It's basically a biological Faraday cage.
That's exactly what it is.
The text explicitly states that the specific function of this double helix formation is to ensure that no disorder takes place.
Yeah.
And that phrasing is fascinating to me because it implies that disorder, entropy, chemical degradation, mutation, that is the default state of the universe.
Entropy is always the default.
Right, and the double helix is an active physical barricade against it. It is holding the blueprints of life in a heavily fortified vault.
It has to, because the information it holds dictates absolutely everything. The text notes that this molecule carries all the genetic information and passes it down from generation to generation.
The master archive.
The master archive.
Yeah.
But it also dictates the real-time development of the organism. It determines whether a cell differentiates into a nerve cell that conducts electricity or a muscle cell that contracts.
Okay, this is where we need to push past the surface of the text a little bit.
Sure, let's do it.
Because stating that a molecule determines cell differentiation is a massive leap. Let's unpack the actual mechanism of that translation for a second. If I'm looking at a twisted ladder made of sugar, phosphate, and nitrogen, I am really just looking at geometry.
Right.
And geometry inherently doesn't contain active instructions. I mean, think of a physical key. It has a specific shape that opens a lock, but the key itself doesn't contain a schematic for how to build the door.
That's a great point.
So how does this static chemical shape actually hold information? How does it function as an active instruction manual?
Well, it operates entirely on the principles of information theory, specifically through sequence and combinatorial logic.
Okay, break that down for me.
The text emphasizes that the sequence of the nitrogenous bases is what determines protein development. It's not about the physical shape of the whole ladder, right? It's about the precise linear order of the rungs.
The sequence itself.
Yes. We have 4 available nitrogenous bases in DNA. If you read them one at a time, you obviously only have 4 options. But if you read them in sequences of 3, which we know as codons, you suddenly have 64 unique combinatorial possibilities.
So you've basically created a complex cipher.
Exactly. The bases are simply a quaternary code,
Right.
very much like the binary code of ones and zeros in a computer program. The sequence of those bases is a literal set of instructions detailing exactly which amino acids need to be strung together and in what specific order to synthesize a particular protein.
So the DNA doesn't actually build anything.
No, it doesn't do the building at all. It provides the cryptographic sequence that tells the cellular machinery what to build.
Wow. Okay, so when the text says that the double helix is designed to ensure no disorder takes place, it literally means preventing any chemical reaction that might flip one of those bits of data.
Right. Because the data is everything.
Because if a single base in a sequence of billions gets altered, if the code gets scrambled, the resulting sequence is going to instruct the cell to pull the wrong amino acid.
Yep.
And you get a misfolded protein.
And a misfolded protein is, at best, totally useless, and at worst, it's highly pathogenic. And this precise vulnerability leads directly to the text's analysis of what happens when that disorder actually breaches the vault.
Right, when the Faraday cage fails.
When it fails. The notes contain a really stark, almost clinical definition of one of our most complex and terrifying diseases. It defines cancer simply as damage to DNA, or interfering with the mechanism of its replication or passing informations.
I was really struck by how mechanical that phrasing is.
It is very cold.
Yeah. We culturally view cancer as this insidious, almost conscious invader in the body, right?
A battle.
Exactly, a battle. But the text strips all of that away and frames it purely as a mechanical failure of the information system.
Just a broken machine.
Yeah. It's an error in the replication mechanism. The machinery copying the code basically stutters, a sequence is corrupted, and suddenly a cell loses its regulatory instructions. It just doesn't know when to stop dividing, so it just relentlessly replicates the corrupted code.
And it forces a massive shift in how we conceptualize the disease. If cancer is fundamentally an information processing error, the corruption of the source code, then the whole approach to treating it has to fundamentally change.
Which is huge.
It is. The text actually concludes its point on cancer by stating, by understanding the mechanism of action of DNA, cancer can be cured.
That is a highly definitive, incredibly optimistic assertion for a scientific document.
Very bold.
Yeah.
It's essentially saying that curing cancer is an engineering problem, not some unfathomable medical mystery.
Right. And that really highlights the philosophical weight of that 1953 Watson and Crick discovery. Once we understood that heredity and cell regulation were dictated by a physical, mutable chemical structure, biology essentially transitioned into an information science.
Completely.
The text is arguing that if we can fully map the mechanism of replication, we can theoretically build microscopic proofreading tools to identify and repair those corrupted sequences.
Or at the very least, shut down the hardware that's executing the bad code.
Exactly. But to understand how that corrupted code actually executes in the first place, we have to look at the process of transcription.
The next step in the chain.
Right, because as we established, The DNA is locked in the vault. It is a highly secure, completely inert reference archive. It doesn't actually synthesize anything itself.
No, it's just the reference book.
So to turn that static sequence into a physical protein, the cell needs an intermediary. The instructions have to leave the nucleus and get to the ribosomes, which are the actual manufacturing centers.
And the DNA double helix is far too massive and, quite frankly, way too valuable to be transported out of the nucleus and fed through a ribosome.
The risk of damage would be way too high.
Exactly. The risk of degradation is enormous. And this is where the second nucleic acid comes into play. Ribonucleic acid or RNA.
RNA. And the text highlights the structural divergence immediately here. We are back to a standard ribose sugar.
Meaning it retains that highly reactive oxygen atom we talked about earlier.
Right, the one that makes it vulnerable to rust, to use our analogy. And crucially, RNA is a single-stranded molecule. It is not a double helix.
Which perfectly aligns with its specific function. RNA is not designed for permanent storage. It is designed for rapid execution and subsequent degradation.
Okay, so it's temporary.
Very. That extra oxygen atom on the ribose sugar makes the molecule unstable on purpose. It is meant to exist just long enough to deliver the message and then be dismantled so the cell can recycle the nucleotides.
That is so efficient.
It's amazing. And being single-stranded means the nitrogenous bases, the sequence data, they are exposed. They are readily readable by the cellular machinery, rather than being locked away inside that tight helix.
It really operates like a temporary execution script in a software environment.
That's spot on.
Like, you have your core operating system, the DNA, safely partitioned away. When a specific function needs to run, the system compiles a temporary script, the RNA, and sends it to an isolated sandbox environment to execute.
Right.
And if the script crashes or gets corrupted in the sandbox, the core operating system is completely untouched.
That is a very accurate way to visualize it. The original text provides a very clear mechanistic flowchart for this entire process. It states that DNA synthesizes and passes instructions to RNA. This is what we call the process of transcription.
Okay, walk us through that.
So the DNA double helix temporarily unzips a very small section of its code, just the specific gene needed at that moment. The cell then constructs a complementary single strand of RNA matching that exact sequence, and then the DNA just zips back up, completely unharmed.
The original reference book goes back on the shelf.
Exactly, like making a single-page photocopy in the library and taking it down to the workshop.
I love that. And then the RNA takes over, and the notes use surprisingly active verbs to describe RNA's role here. It says RNA receives, reads, decodes, and uses the given information to synthesize new proteins.
Very active.
Yeah, it frames RNA not just as a passive messenger pigeon, but as the active foreman of the cellular workshop. It is the entity actually interacting with the amino acids and directing the assembly based on that decoded sequence.
RNA is the true interface between the abstract information of the genetic code and the physical reality of the organism.
Right.
But, and this is a massive but, this elegant relay system, from immutable DNA to temporary RNA to physical protein, it has a devastating flaw.
Which the text explicitly details.
It does. The system is fundamentally agnostic to the quality of the information it is processing. It only knows how to copy and execute.
It doesn't fact check.
It absolutely does not fact check.
It's the chain of cascade failure. The text lays out the mechanism for genetic diseases very clearly. Quote, errors introduced into the genes synthesize faulty RNA. It synthesizes faulty proteins that do not function the way they are supposed to. This disorder causes genetic diseases.
The machinery is flawlessly executing a broken schematic.
Flawlessly executing a broken schematic, yeah.
If there's a mutation in the original DNA vault, let's say a missing base, an extra base, a swapped base, the transcription process is just going to faithfully copy that exact error right into the RNA.
And the RNA foreman, who has no ability to proofread against any sort of external logic, simply reads the corrupted sequence and builds the protein exactly as instructed.
Exactly. And because proteins dictate nearly every structural and catalytic function in the human body, a single misfolded protein can result in devastating conditions. Cystic fibrosis, sickle cell anemia, Huntington's disease.
All from one typo.
One typo. It's a chilling realization of just how fragile the entire architecture really is. All of this immense complexity, all of these billions of nucleotides functioning in perfect, beautiful concert can be completely undone by a microscopic typo.
It really emphasizes the sheer biological cost of disorder. But, up to this point in the notes, we have been looking at a completely closed system.
Right. Entirely internal.
The DNA, the RNA, the ribosomes, this is all internal cellular machinery. It is the ultimate self-contained manufacturing plant. But no manufacturing plant can operate in a complete vacuum.
What's
Right?
possible?
It requires raw materials and regulatory catalysts imported from the external environment.
Which brings us to the massive paradigm shift detailed in the second half of these notes. We move from the sort of eternal abstract mechanics of the nucleotide to a very specific, tangible turning point in scientific history. The year 1912.
1912.
The text introduces Hopkins and his discovery of vitamins. And what is vital here for you to understand is the mindset of science before this discovery.
Right, context is everything.
The text notes that previously, nutrition was thought to rely solely on carbohydrates, proteins, and fats.
It was a very macroscopic view of biology. In the 19th and early 20th centuries, nutrition was viewed almost entirely through the lens of thermodynamics, right?
Yeah.
And basic mass.
Calories in, energy out.
Exactly. You consumed carbohydrates and fats for combustion and energy, and you consumed proteins to replace physical tissue. The body was viewed as a very simple engine. You put in the fuel, it burns the fuel, it runs.
Which is a very intuitive way to view health, honestly, because it deals with the things we can easily observe and measure.
Yeah, it makes sense. If you're starving, you lack calories.
Right. But the text shows how Hopkins completely shattered that simplistic view. He identified that normal growth required what he called other substances in incredibly small quantity.
The realization that health is not just about fuel, but about trace regulatory mechanisms.
Trace being the key word. Hopkins initially called them accessory growth factors.
And I have to say, that phrasing, accessory growth factors, it is incredibly revealing of the era's skepticism.
It really is.
Calling something an accessory implies it is secondary, right? A biochemical luxury. It suggests that the core engine runs on carbs and proteins, and these tiny factors just, help it run a little bit smoother.
Just a nice to have.
Exactly. It took years for the scientific community to accept that these microscopic invisible trace elements were not accessories at all.
They are absolute non-negotiable catalysts. The text mentions that a little later, a scientist named Funk proposed the name vitamin for these substances, discovering vitamin B1, which is thiamine.
Vital amine vitamin.
Right. And the shift in language from accessory to vital amine or vitamin marks the exact moment human medicine realized that the internal cellular machinery we just spent so much time discussing, it is completely paralyzed without these external chemical keys.
So you can have the perfect DNA sequence, you can have flawless RNA transcription, but if the RNA foreman doesn't have the specific vitamin coenzymes needed to actually facilitate the chemical reactions to build the protein, the entire assembly line just grinds to a halt.
It totally stops. And that introduced the whole concept of the deficiency disease.
Which was revolutionary.
It was.
Yeah.
Before this, a disease like scurvy or pellagra was often attributed to, infectious agents or vaguely defined poor constitutions.
Bad air, things like that.
Yeah, exactly. The vitamin paradigm proved that you could be consuming 5,000 calories a day of refined carbohydrates, having all your energetic needs completely met, and still suffer systemic biological collapse simply because you lacked a few milligrams of an invisible organic compound.
It proved that human biology is inextricably linked to the diverse chemistry of our external environment. We cannot synthesize everything we need internally. We essentially outsource the production of certain essential catalysts to plants and other animals.
We did.
And if we are cut off from that external supply chain, we break down.
And the text is very careful here. It does not present vitamins as a universally benign magic bullet.
Right. More is not always better.
Definitely not. It introduces a critical physical categorization, which is solubility. Specifically, the notes focus on the fat-soluble vitamins A, D, E, and K.
And this distinction between water-soluble and fat-soluble is where the mechanics of biology become incredibly dangerous if they are misunderstood.
Very dangerous.
Because a water-soluble vitamin like vitamin C is highly transient. If you consume 10 times the amount of vitamin C your body actually needs, your kidneys simply filter the excess out of your bloodstream and you excrete it.
Right, you just pee it out.
Right, the body maintains equilibrium by just flushing the system.
But the fat-soluble vitamins operate under completely different biochemical rules. Because they dissolve in lipids, meaning fats, they integrate into cellular membranes and are stored in adipose tissue, which is the body's fat reserves.
So the body cannot easily flush them out via the kidneys.
No, it can't. They accumulate.
They accumulate, which brings us all the way back to that horrifying paradox we started the show with.
The vitamin D.
The vitamin D. The text explicitly states, quote, if these vitamins are taken in large quantity, they accumulate in the body and cause diseases. It highlights vitamin D specifically, noting that accumulation causes bone pain and bone-like deposits in the kidneys.
Hypervitaminosis D. It is the absolute ultimate manifestation of biological imbalance.
Walk us through how that actually happens chemically.
So vitamin D's primary physiological role is to facilitate the absorption of calcium from the gut into the bloodstream. It maintains the precise calcium gradients you need for bone mineralization and basic cellular function.
Okay, so it's basically the foreman in charge of the calcium supply.
Exactly. But if you accumulate too much vitamin D in your fat tissues, it relentlessly signals the gut to just keep absorbing calcium, regardless of whether the body actually needs it.
Doesn't know how to turn off.
It doesn't. So you develop hypercalcemia, which is an excessive concentration of calcium in the blood. And calcium is highly reactive. When the concentration gets too high, it physically begins to precipitate out of the blood and crystallize inside soft tissues.
It literally turns the kidneys into stone.
Yes.
The very mechanism that evolved to ensure you have enough calcium to build a strong skeletal structure basically goes rogue, goes into overdrive, and begins calcifying the filtration organs that keep you alive.
It is a stunning example of how a microscopic failure of regulation, and in this case, an environmental excess rather than a genetic deficit, results in catastrophic macroscopic disease.
It really forces us to view the human body not as a static object, but as a hypersensitive, continuously calibrating chemical equation. The margin between optimal health and lethal toxicity is entirely dependent on maintaining the precise molecular ratios of these specific compounds.
Which perfectly ties the two halves of these notes together, don't you think?
Completely.
Whether we are talking about the internal quaternary code of the DNA double helix or the external trace accumulation of a fat-soluble vitamin, life is fundamentally an exercise in resisting disorder through perfect microscopic balance.
The architecture is simultaneously incredibly robust, capable of passing genetic information down across millions of years, and incredibly fragile.
Capable of being entirely derailed by a single corrupted nucleotide or a few excess milligrams of a lipid-soluble catalyst.
It's a lot to process. The notes we explored today take us from the abstract geometry of the nitrogenous base through the mechanical reality of cancer and genetic disease, all the way to the historical realization that our survival is tethered to invisible environmental chemicals.
A wild ride.
But before we wrap up this deep dive, the text leaves us with a fascinating, kind of unstated corollary regarding the future of how we interact with all this machinery.
It really does. The text provides all the logical premises for a massive leap in medical technology.
Right. We discussed the text's assertion that understanding DNA's mechanism could cure cancer, essentially fixing the vault. But we also mapped out the transcription process where the immutable DNA vault sends out the disposable single-stranded RNA messenger to build the proteins. So, if genetic diseases are caused by the RNA faithfully executing the vault's corrupted instructions, it raises a profound question about medical intervention.
Where is the safest, most efficient point to actually intervene in that cascade of failure?
Exactly. Attempting to physically unlock the DNA double helix inside the nucleus of a living cell, excise a corrupted sequence of bases, and splice in the correct sequence without causing, catastrophic off-target disorder, that sounds like an incredibly dangerous, high-risk endeavor.
Very risky. The vault is designed to resist tampering.
But the RNA is not in the vault.
No, it's not.
It is a temporary single-stranded script operating out in the open cellular workshop.
So the thought experiment naturally follows, right? Instead of trying to permanently rewrite the heavily guarded master archives, could we simply flood the cellular workshop with interceptors?
Could we design synthetic molecules that recognize the specific corrupted sequence of the faulty RNA and just bind to it, neutralizing the script before the ribosome can ever read it and build the pathogenic protein?
That is the big question.
You aren't curing the genetic defect in the vault. The DNA is still technically broken, but you are functionally curing the disease by perpetually intercepting the bad instructions before they execute.
It bypasses the need to edit the core operating system entirely.
Right. It uses the system's own modularity, that separation of long-term storage and short-term execution, as the therapeutic vector. It's an incredibly elegant theoretical solution derived entirely from the mechanical flowchart the text provided.
It fundamentally reframes what it means to cure a genetic disorder, shifting from permanent architectural repair to continuous informational interception.
I will leave you all to ponder the implications of that kind of biological control. We have barely scratched the surface of the complexity operating inside every single one of your cells right now, but hopefully these notes have given you a new framework for understanding the incredible, precarious balance that keeps you alive. Thank you for joining us on this deep dive. Keep questioning the mechanisms behind the macroscopic world, and we will catch you next time.